And I'll be back later on too, but not this afternoon. Today we're moving on to engineering considerations and optimal systems design, where yesterday we spoke mostly about plants and plant production and nutrition and insects and all that stuff that should get you excited as a grower. But to be a good grower, you need to have good hardware, you need to have systems that work together well, that you can afford to not only purchase but operate in a cost-effective way. So today there'll be this morning there'll be 4 presentations along this subject lines. And our first speaker is Dr. Murat Kacira, my colleague at the Controlled Environment Agriculture Center and in the Agricultural and Biosystems Engineering Department. He knows sensors, he knows controls, and he's going to talk about monitoring your greenhouse environment and developing technology trends to do so. So, Murat, I've held him off long enough. I think it's your turn.
I hope I can stay still on this platform. All right. Thank you very much, Gene, and good morning, everyone, and good to be with you this morning, and I hope you had a beautiful day yesterday with exciting presentations, and I hope you had some time to enjoy the evening and the beautiful weather we have here in Tucson and what offers for you. Some of you may be coming from cold places, so I hope you will enjoy Tucson this week. And I'm looking forward to actually this week and interacting with you and discussing about your interests and your applications and your questions. So please feel free to come back and questions, and I'm also around this week to discuss with you. So yesterday, the discussions and the presentations focused more on the fundamentals and the needs of the crop. And today, with my talk, I'm going to discuss with you briefly about some of the tools that a grower can use and to make the production better or improve the quality and the quantity in the production while saving resources. And these tools could be as simple as a thermometer, or it could be a sensor, it could be a simple sensor, it could be a sophisticated sensor, communicating with devices, instrumentation to help the grower to improve the management and other practices in food production in controlled environments. But I would like to say a couple of things first at the beginning of my presentation rather than wait till the end. The production success in controlled environments really relies on the capabilities and the skills of the grower. And then if we equip the grower with instrumentation tools, then we can really help the grower to do a better management. Crops are affected by their surrounding environment. There are a lot of processes, physiological processes, physical processes occurring, and that affects the plant and also the plant performance. Photosynthesis, the basis of life, the physiological process converting light along with CO2 and generating usable chemical energy. And the respiration is the opposite of photosynthesis, basically taking the food in the form of carbohydrates and fats and releasing CO2, water, and energy. Plants need this process as well. Transpiration, it's the evaporative cooling mechanisms of plants. It's the evaporation and water diffusion from plants to their surrounding environment, and the plant transpiration process also affects the way the plants also uptake nutrients from the root zone environment. The leaf and fruit temperature is affected by the surrounding environment, and that also affects some of these processes, as you see on the slide. Root zone environment has a direct effect for plant response and on the growth of the plant. The pH levels, electrical conductivity, dissolved oxygen. Yesterday, Gene talked about it and Merle talked about it. temperature. And then, in turn, the overall yield and quality of the production is affected because of these interactions of plant with the surrounding environment. There are key variables, as you can see, that affects the plant production. And these are light, air temperature, the water content in the air, carbon dioxide levels, the pH, EC, dissolved oxygen, all of these factors. And I'm going to go through a couple of these and describe them, as well as some of the tools and measurements and units associated with these key environmental variables. Light is one of the most important and fundamental key variable that affects plant growth and the production yield and quality. When you look at the global radiation penetrating into the greenhouse environment, you can see that we can divide that into three main components. And these are the ultraviolet radiation, the photosynthetic active radiation, and the radiation that comes in the near infrared wavelengths. So just talking about these individually, we can talk about visible light. That is the wavelength that we can see as humans, actually, is a range between 380 and 780 nanometer, and this is the wavelength is essential for the development and plant growth. But plants actually are mostly affected by the photosynthetic active radiation that is between the 400 to 700 nanometer range. The intensity of the light, the duration of the light, and the spectral distribution of the light affects plant responses. And the UV light, and that's in the range of 280 to 300 nanometer, is generally detrimental for the plants, but if it is strategically used, and we can get benefit out of UV light, and maybe to enhance the look or the color, the pigmentation, or the secondary metabolites, nutritional level of the crop. The near-infrared radiation and the radiation in the range of coming in the range of 700 to 300 nanometer increases crop and greenhouse temperature. Some of this radiation is reflected through the glazing, some of that is absorbed, and the remaining part penetrating into the greenhouse really increases the temperature of the greenhouse as well as the crop. And because of that, we need to open up vents, and the CO2 can be also escaping from the greenhouse, so it has an direct effect in the climate in the greenhouse and also on the plant. This radiation in the near-infrared wavelengths is desirable during the cold periods because it helps to reduce the load for heating, but it is undesired during the warm period as it adds to the loads for cooling demands. And there are agents that you can use to actually manage the near-infrared radiation and how it's penetrating into the greenhouse or how it can be reflected. So when you look at this overall range of wavelengths, the range between 280 to 2800 nanometer, it is termed as global radiation or shortwave radiation. And beyond 2800 nanometer, it is basically the long wave radiation. So when it comes to light, it has thermal effects, light intensity, quality. The photosynthesis process is affected by light intensity and quality. The morphology of the plant is affected by light quality and also the direction of the light, for example, tropism. Photomorphogenesis is affected by light quality, and also the duration of the light affects that process. And before we talk about measuring the light, we need to also describe how we present the light or what units we use. And there are two main terminologies or terms used in terms of the units. One is in terms of photometric terms. And you will see commonly sensors used to measure, lux or those measuring the photons, but those measuring in terms of, for example, candles, food candles or logs are pretty much referring to the light, and that is sensitive to the human eyes. So you may be measuring the light using a lux meter, and under different light sources, then the sensor may give you the same amount of food candles or logs. But when you go and look at the photosynthetic active radiation, that might be totally different. So we need to use a sensor that is actually giving the light information or important information for light for the plants, not for the human, those sensitive to the human eye. So these are the terms used in photometric terms when you describe light. And those are those units of light described in radiometric terms. For instance, radiance, a light or the power of light that is received or that is seen in a unit of volume, or how concentrated light might be your interest by looking at a light that is coming off of the light source. So when you're talking about a power of light that is coming from a point source, we talk about radiance, and the unit for that is watt per solid angle steradian and per unit area, which is per square meter. But when we talk about the light that is seen on a surface, as you can see, the light incident on the surface, then we talk about the irradiance, and that is the power of light per unit area basis. So the unit is energy per second, joules per second, that is power, the watts per unit area basis. So here what I want to stress is, again, we need sensors that we can use the term or the units that is important for the plants, not for human eyes and sensitivity. So what to measure when it comes to light? Do we want to measure the light at this point right now and the intensity of it versus maybe the light that plant sees over a course of time, and how, which one is more important? Well, both are important actually. So when it comes to light intensity, for plants, as I mentioned, the photosynthetic active radiation in the 400, 700 nanometer range is more important because the photosynthesis is a quantum process. So the chemical reactions in photosynthesis really affected by the number of photons that are falling onto the crop or crop canopy rather than the energy of that photon in a given wavelength. So if you really talk with plant scientists, they really like to use the photosynthetic photon flux density in terms of the amount of photons falling onto a unit area per time basis. So the units is micromoles meters squared per second to represent the light at that instantaneous time period. And you can see in this famous graph here showing the relative response of the plant in terms of photosynthetic efficiency of the plant in different wavelengths after Mach-3. And as you can see, the plants are doing much more efficient job in terms of photosynthetic efficiency at the blue and red wavelengths because of the absorption of chlorophyll A and chlorophyll B. But we can also look at accumulated light over the course of the day, which is also important for plant and plant productivity. So you can imagine using an umbrella or a collection pond and trying to accumulate all those photons falling onto that umbrella. At the end of the day, you look at the amount of photons that was received in that per unit area basis. So you can go from a micromoles meters squared per second reading of photosynthetic active radiation to a daily light integral, which is the integration of those moles of light falling onto a given area per second basis. The plants are different in terms of their needs for daily light integrals. So those are crops needing the light in the range of 3 to 6 daily light integral. Those are low light crops. 6 to 12 medium light, 12, 18 high light crops, or higher than 18 moles per day per meter square basis DLI requiring plants are the very highlight crops. So for lettuce between 12 to 17 daily light integral is an optimal range. If you go at 17 or beyond, we need more dynamic boundary, more turbulent flow in the boundary layer to really enhance the transpiration process and to minimize some of the crop disorders that you would see or you would actually experience producing lettuce under those highlight intensities. Tomatoes and cucumbers are highlight crops, so anywhere between 20 to 30 DLI is an optimal range for these crops to perform. So what sensors you can use to measure photosynthetic active radiation? Quantum sensors are used to measure photosynthetic active radiation between 400 to 700 nanometer range. If you're measuring light under sunlight or those traditional supplemental light sources such as high pressure sodium light, then the sensors, the quantum sensors that are mostly available in the market will give you an accurate reading. But if you're using a light source that is under a specific wavelength, such as with LEDs, then you really need to find a sensor, a quantum sensor, that is calibrated, that is designed to perform and respond to the whole wavelength between the 400 to 700 nanometer range. So looking at the relative response of a given quantum sensor, as you can see here, in part, for example, this sensor with this response, with the black one, is only sensitive up to 610, 620 nanometer wavelength, which is just at the edge of red. So if you're using a red LED source, then this sensor may not be really sensitive or provide you accurate readings under that sort of LED lighting. But there are also sensors in the market that are better, that provide better response to all the wavelengths in the 400 to 700 nanometer range. You can make a decision in terms of which type of sensor you would like to buy. These quantum sensors are connected. Some of them are connected to a meter, so you can really go out and make the measurement and come back. And some of these sensors have data logging capabilities, so you can log the data and then extract the data later on. Or you may prefer actually buying the sensor itself with the cable. And if you're a little bit familiar with the instrumentation and or if you have someone in your team to understand the instrumentation, then you can maybe connect the sensor to a data logger yourself and go through the programming to be able to perform different applications with that sensor, in addition to not just monitoring, but also use it maybe for control applications. There are other types of simple sensors out there that helps you to determine data light integrals. For example, this particular sensor that I was able to run into in the market out there, it's a portable sensor that it has a nail here that you actually insert in different or position in different locations in your production space. And the sensor, with a push of a button, accumulates the daily light integrals at the end of the day, and then you just go and take a look at your daily light integral with that particular sensor. In addition to daily light integral, it also provides the average photosynthetic active radiation for you to look at. So depending on your interest in that production system, you may actually deploy several of these sensors in different locations and look at maybe the uniformity of light distribution in that environment. Or if you have hanging baskets like that, you can put one sensor around that hanging basket and look at the shading patterns and, to see if you need to improve something in terms of your management and production practices in that environment. But there are also other, a little bit more sophisticated sensors available to monitor not only other key variables such as air temperature, humidity in this shielded, aspirated enclosure, but also a quantum sensor is integrated to this small weather station with data logging capabilities and also data analysis capabilities to integrate the photosynthetic active radiation and also present you or log for you the daily light integral. You can, if you have a photosynthetic active radiation sensor or a quantum sensor that measures PAR, then to be able to determine daily light integral, what you can basically do is to deploy that sensor and keep measuring the photosynthetic active radiation. Say for a 15-minute interval, you have an average PAR reading that is representative of that light intensity during that 15-minute time period, and you record that. And you keep recording the photosynthetic active radiation over the course of the day, and that's what you would see, for example, on a given day like this. Then you have all these 15-minute average photosynthetic active radiation. Then what you can do is to actually integrate or add all the PAR readings in that 15-minute time interval, and then multiply that by the delta T, which is in terms of seconds. So 15 minutes times the 60 seconds, you have 900 seconds times all that PAR data you accumulated over the course of the day, and that you need to convert into, so that's the total amount of micromoles meter square per day, and then you need to divide that by 1 million, which is the conversion from micromoles to the moles. So when you do that calculation, simple calculation, you basically determine the total daily light integral in terms of moles per meter square per day. So this is something that you can do by using your by using your quantum sensor. Now, more sophisticated applications we're seeing in terms of the management and control of the supplemental lighting systems. For example, some of the environmental control systems you would see out there are now integrating or has been integrating quantum sensors and measuring it and analyzing it in a way that you have more dynamic control of the supplemental lighting. These systems basically looks at the historical data to predict what would be an expected daily light integral or the photosynthetic active radiation for a given day, with a sensor, actual sensor, quantum sensor, providing the feedback to look at the gap in terms of how much supplemental lighting you need to provide in that environment to really hit that daily light integral target in that application. You can do this also in terms of different time periods, days, or for a seasonal adjustment of daily light integral. So there are systems like this, both for greenhouses or for those using LED lighting, supplemental lighting, and other types of controlled environment agriculture systems. So that's the units and sensors for quantifying light in terms of the photons and per area, per time basis. In terms of the energy, when you talk about the energy of the light, when you talk about heating, cooling loads, you know, the way we engineers do, we look at the light in terms of different units. For example, the power of light or the energy of light per unit area per time basis. So the unit for that is watts per meter square to represent the light in that instantaneous moment. But we can also accumulate that light or integrate that light to look at the daily integrated solar radiation in terms of energy units. And the unit for that is, for example, megajoules per meter square. So the sensors are slightly different compared to a quantum sensor. Here, those with the conversion of thermal energy to electrical energy or electrical signal, for example, thermoelectric based global radiation sensor or shortwave radiation sensors, as you can see here, covering the whole range, the full range from 280 to 2800 nanometer range. versus using photodiode-based sensors, as you can see here, measuring or the sensitivity from, say, 300, or as you can see, different models have different sensitivities from 400 to 1100 nanometer range, which kind of represents about 95% of the total global radiation within that range, but still calibrated against a pyranometer measuring the radiation in the full spectrum. So they are highly accurate. They are highly accurate to represent the global radiation for the full range. There are some other models available also on the market using thermopile-based measurement with a fraction of cost compared to traditional thermoelectric-based sensors, as you can see here. So you need to decide on what type of measurement you would like to perform, the accuracies you want from a given sensor, and also the cost will play a role at the end to make a decision. When we talk about light quality, and if you're interested in the spectrum, the full spectrum, under, for example, supplemental lighting applications, then a spectroradiometer sensor is used to look at the full spectrum of the light. Air temperature, humidity, these are the key variables also that we need to be measuring. And the sensor could be as simple as a liquid and glass thermometer to look at maybe the minimums and maximums on a particular day, just to have an idea about those, the lowest and highest points in the day. Or you can actually take a psychrometer like this to measure the wet bulb and dry bulb temperature, and maybe calculate your relative humidity and have an idea about, the water content in the air. These are very simple, low-cost sensors, but you can also make your own sensor if you want to enjoy working with the instrumentation. So you can take two thermocouples, one measuring dry bulb temperature, one measuring wet bulb temperature with a wetted, wick on it, and then connect that to the data logger to monitor the temperature in real time. There are also small data loggers, microcontrollers available that a grower can use. You will need to decide what type of application, again, what type of resolution that is required when making these measurements, air temperature, humidity measurements. Some of these data loggers have capabilities to measure the air temperature, humidity, for example, in milliseconds. But is that the range you want? For a grower, actually, every 15-minute data is a good, resolution to look at these environmental variables. So if you have a lot of data, then it brings also the need for more data mining, more data analyses, and it requires more space, more memory, and it may add up to the cost as well. So there are also microcontrollers available, very low cost, out there that you can maybe do the things on your own and build sensors on your own. When it comes to air temperature and humidity measurement, we need to pay particular attention to first, not only with these sensors, but also with other sensors, to position the sensors closer to the canopy, at the canopy level where really the climate or microclimate is really important for the plant or plant physiological processes or the exchange of processes between the plant and the surrounding environment. So the sensors should be positioned in the canopy level. With air temperature and humidity measurements, we need to have proper airflow around the sensor so we can minimize the error. For example, if you're measuring the temperature, we don't want to have direct sunlight hitting on that sensor to create errors. And also with proper airflow, that helps to improve the accuracy of the measurement. So aspirated, shielded sensor needs to be used. When you're measuring the light, for example, the sensor must be positioned in a place where there's no direct shadow hitting on the sensor, and the sensor must be cleaned, kept clean to improve the accuracy of the measurement. So we have a more representative measurement of the light over the course of the day. Yesterday, several speakers talked about relative humidity, vapor pressure deficit, why it is really important to have an idea about vapor pressure deficit, which is basically one of the main driving force for the transpiration process. That is the pressure difference. Vapor pressure deficit is the pressure difference between the saturated vapor pressure and the actual vapor pressure. So if this is a psychrometric chart that Murat showed you yesterday, it's a simple chart actually presenting you the moist air properties, dry bulb, wet bulb, dew point temperature, absolute humidity of air, or the energy of the moist air in one single chart. And this chart basically can be used, for example, to look at your data. Several speakers again talked about yesterday your climate, your environment that you have, and what type of cooling systems you need to, for example, consider. In locations where the humidity is high, the temperature is high, then we don't have so much capacity to cool using evaporative cooling systems, for example. So you can use a chart like this to actually log all your outside climatic data, hopefully historical data, some average, temperatures and maybe humidities in your location. And if you figure out that if your data is kind of falling into this region over here, that means that you are really having high temperatures and with high humidities, then as you can see, you're so close to the saturation line here where you don't have a cooling capacity with that system. Or a cooling system with fogging or fed and pan-based systems. But if you're over here, like our climate here, for example, so we have so much capacity, so much room actually to reach to the saturation point and reduce the air temperature. So this tool, this chart can help you to look at these variables. So the vapor pressure here, again, the difference between the saturation vapor pressure at 100% relative humidity versus the actual vapor pressure that you would see here, so the gap between the two. So when it comes to plants, transpiration, and quantifying the water content in the air, we prefer this measurement over the relative humidity measurement, which is basically a relative way of quantifying the water content in the air. That basically tells us how much the air has water in that moment versus how much that air can hold at the given or the same dry bulb temperature. So it's a relative term. All right. The charts like this are also helpful, and a version of this, actually, you saw this from Murat's presentation, presenting you the air temperature and relative humidity and all the vapor pressure deficit based on those two environmental variables to see where your climate actually falls in. So the green portion of this chart is basically showing a vapor pressure deficit in the range of 0.4 to 1.2 kilopascal range. And this is a range, actually, which is comfortable for majority of the crops that are grown in controlled environments. So you can log the data and then look at the hours that you have with this type of vapor pressure deficit ranges to determine what type of adjustments you need to make or controls you need to add or manage in your operation. This is the chart that is showing the water content in terms of pressure units when it comes to vapor pressure deficit. But when you're traveling to other countries, such as Europe, and growers prefer using the humidity deficit when it comes to referring to moisture content in the air. It's basically the same thing, but in this case, we are actually representing the total mass of water per unit volume of space. So the unit is different, but you can convert from the pressure units into the mass units for quantifying water content. Measuring crop temperature can be an important information, for example, providing you about the health and the crop, how the crop is performing or growing in that given environment. Murat talked about touching the plant or making love with the plant. So, the plant temperature can tell something about the health status of the plant. So there are devices such as infrared guns that can be used to make a direct measurement from the plant or root zone environment, or maybe equipments that you have in that environment to have an idea about the status of the plant or the instruments or devices used in that production space. When it comes to measuring the surface temperature, canopy temperature with infrared transducers or infrared guns, particular attention must be paid to the field of view of these sensors, because they have a particular field of view and they see everything under that field of view and then average the reading for you. So if the sensor is not positioned properly, in addition to measuring the plant temperature, you may be also looking at the background temperature and making an average reading. So we need to really look at the specifics of that sensor. Measuring pH and electrical conductivity is very important, because the substrate, the fertilizer, or nutritional management really relies on knowing what are the levels of pH and electrical conductivity in the soil, if you're using soil media, or if it's water culture system, what's the pH and EC levels in the nutrient solution environment. And pH, for example, has a direct effect in terms of how the certain elements are available for the plant or taken up by the plant. So you can actually maybe buy a sensor, a handheld sensor, to measure electrical conductivity, and maybe two together, the pH and electrical conductivity in one single sensor, maybe to keep the cost down. You can look at the accuracies and resolution, the cost to make a decision in this decision making. But there are also advanced systems that measure electrical conductivity and pH to make proper adjustments to control the fertilizer injection or nutrient injection to the plants. Those, for example, using concentrated solutions of nutrients and maybe diluted acid solution, using peristaltic pumps to inject these solutions and mix it with water based on a sensor feedback, as you can see here. Or you can find more sophisticated maybe systems where you have more integrated, more distributed monitoring and control capabilities when it comes to nutritional management. Measuring carbon dioxide is really important in the growing environment because CO2 is important for photosynthesis, and it is an important variable, especially under the light-independent conditions when it comes to photosynthesis. So the graph here is basically showing you the light response curve for a crop or for a leaf under different light intensity levels, as you can see here. So the plant actually reaches to a light saturation point, and beyond that point, there's no effect of adding more light to increase the photosynthetic rate. But under these conditions, under light-independent conditions, as you can see, the availability of CO2 can be an important consideration. Maybe to increase the CO2 to enhance the photosynthetic rate might be advantageous things to do. Of course, there are other factors to look at in this exchange process. In this process, the light, the nutritional level, or the temperature, the nutrient availability also plays a role in terms of managing the CO2 levels. There are simple sensors that can be used to monitor CO2 levels, or again, more integrated, more advanced sensors as part of a climate monitoring and control system can be considered to manage CO2 and the hardware associated to manage the CO2 fertilization. Measuring water consumption and drainage can be an important, actually, measurement for you to make a decision. It can be as simple as maybe monitoring the water that is coming into the plant, maybe from a drip emitter, as you can see here. So you can accumulate the water on a given day, and then maybe using a collection catchment tank here to look at the amount of water that is being drained. And by looking at the difference between the two, you can have some idea about how much water the plant is consuming, or maybe adjust the drainage rates, a certain percentage of drainage that you need to achieve for the plant to make sure that the plants are actually growing better or have access to that nutrition properly in that production system. So these are the things that you can maybe simply do it yourself, but there are also other advanced technologies out there that monitors this water consumption in real time by using lysimeters and load cells and measuring not only the crop and the crop growth and give you that information as well as how much water goes in to the plant or how much is drained. And even with sensors, electrical conductivity and pH sensors or other sensors integrated into the input and drainage water to give you a full range of measurements for you to improve your production and management applications. Growing moisture media, water content can be performed using different types of sensors. I hope to go through some of these during our sensors and control session during Thursday also. So these are the types of sensors these are the capacitance-based sensors. They basically look at how good a media is in terms of holding the electrical charge or conducting an electrical charge, and that is related to the amount of water content in that growing environment. So there are different models, different types, not only providing the moisture content in terms of volume basis for you, but some of these sensors also provide electrical conductivity as well as temperature of the growing environment for you. And they can be connected to a handheld device or meter to give you the data, provide you the data, or you can connect these sensors to the other types of instrumentation or data logging devices to perform the measurement. There are wide ranges of environmental monitoring and control systems out there, as simple as a thermostat to a do-it-yourself type of devices, those with the medium tech operations, or maybe for more integrated, more distributed applications. Fourth Industrial Revolution has been building upon the Third Industrial Revolution, the precision agriculture with the Third Industrial Revolution, but with the Fourth Industrial Revolution we are seeing the fusion of the physical environment with digital and biological environment using technology. So with this approach, actually, we're seeing more interest and focus on resource use efficiency rather than just focusing on the yield or how much kilograms of produce you can achieve. Rather than doing that, we're also looking at how much resources we're putting into the production. Automated crop diagnostics and decision support systems are among emerging automation systems and technologies where the sensors are used, for example, computer vision systems to look at information from the plant in addition to those we measure from the aerial environment to make improved decision. If you enable the grower with this type of information, those coming directly from the plant, for example, in addition to other environmental variables, then we can really improve the resource use efficiency in the production and also the quality. Digital eyes on the plant's in control as an aid or help to the grower to make a better decision. Here's an application that actually we conducted as part of our research in our lab. And our next speaker, David Story, Dr. David Story, I had the pleasure to working with him, and maybe he can describe this in a little more detail in this presentation, constructed a multi-camera based system where you can not only look at the color, but the texture and temperature information on the plant and provide the user a final image where a troubling spot or anomalies might be present in that production system to further look at the plant canopy. So these type of plant response-based sensing systems are gaining interest as part of the integration to environmental control applications. Being able to control the light, for example, supplemental light, based on direct information coming from the plant using biofeedback-based control is an interest for us, and there are a lot of potentials actually in this area and the growth for light management. Now the production systems are more data centric, and we have a lot of data, big data sets that is available but not all of it is used and utilized to make a decision or for control and management applications. So data analytics, dashboards, and decision support systems are actually becoming more available and accessible and interesting, and there's a trend and growth in that area. This is a system that actually we developed in our lab to control and monitor and make some decisions for our vertical farming facility. We're going to go into details of this when you're visiting our vertical farm on Thursday. Internet of Things, or Internet of Everything, is kind of distributed sensors, objects, communicating information for remote monitoring and real-time monitoring control applications. Accessibility to data through cloud-based services is becoming a trend and an area that is growing and can provide actually direct connectivity between the user and among the users over a given network space. And this would really help managing the data with a lower cost and a more effective way for crop production in controlled environments. And looking at the data, the historical data from the past, looking at the current data, and maybe using some predictive modeling from the physical environment, from the plant and the greenhouse system. On top of that, using maybe market or the sales or the economic information into this data platform to make a more intelligent decision is important and becoming available and really strong a tool to improve the production and profitability. Our next speaker, again, David Story, is going to touch on that in more detail and go into business intelligence and how they use it for labor management practices. So I believe this is what I have for my presentation, and I'll be happy to answer questions now or maybe during the discussion session. Thank you.